In the past, we've looked at how computers represent data and how computers perform arithmetic and how we can duplicate that arithmetic on paper. What we want to do now is start to look at the internal circuitry behind how computers perform those operations. And to do that, we need to look at a couple things. We're going to look at how we represent the logical functions that are operated on using Boolean algebra. And we're going to look at the equivalent of those using digital logic gates. To begin with, we need to understand the basic Boolean logic functions. And these are mostly ones that you are familiar with from whatever high-level language you've programmed in before. When you write if statements, you can write a simple if statement that has a single condition. But when you write an if statement that has multiple conditions, such as if age is greater than 17 and less than 29, we're effectively using an analog to these Boolean logic functions. But at the digital logic level, they perform something a little bit differently, and we'll get to see that here. So the first of these functions is the AND function. And just like the way you're used to using AND in code, the AND operation has multiple operands that we'll call inputs, and the AND function is going to return true only when all of those inputs are also true. The OR function will take all of its inputs, and if even a single one of those is true, then it's going to produce a true output. And that works for us the same way, whether it's a Boolean algebra expression or whether it's a piece of digital logic that's equivalent to that. In other circumstances, it will produce false. So the OR gate generally produces true, and really the only time it produces false is when all of its inputs are false. The third is the NOT function, or the inversion function. And what this does is it takes its input and then produces as output the logical opposite. So if you get a true value or a 1 coming in, you'll get a false value or 0 coming out. If you get a false value coming as input, you will get a true value or 1 coming out. And this is a particularly interesting gate because it can be implemented with a single transistor. Now the last of the main Boolean functions is exclusive OR. This is one that typically only has 2 inputs, but on occasion you will see a multiple or a exclusive OR function or gate that has more inputs than 2. Generally speaking, the way to think about these is that the exclusive OR function will produce true output only if one and only one of its inputs is true. So if 2 inputs or more are true, or no inputs are true, it will produce false. Now on some occasions when there's more than 2 inputs, I've seen this implemented as kind of a cascading series of 2 input exclusive ORs. So there's 2 inputs up here that go into a single exclusive OR and produce 1 output. That output is fed into a second exclusive OR with a third original input. And so that gives the effect, in a sense, of having a 3-input exclusive OR. However, this does not produce the same logical output as true when one and only one of the original inputs is true. Instead, when you do a cascading series of exclusive ORs, what you're going to end up with is something that produces a true output if an odd number of its inputs are true. Now, there are secondary Boolean logic functions as well, and they can be synthesized from the originals, or from the main Boolean functions. The first of these is NAND, which is effectively just inverting the output of the AND operation. So it's fairly simple. The same is true with NOR and exclusive NOR. They are the OR operations inverted, or the exclusive OR operation with its output inverted. Now, in this slide, you'll notice that I talk about the inputs being true and the outputs being true. And prior to this, when we looked at binary values or data representations, we're constantly talking about zeros and ones. So the computer stores these zeros and ones in a fashion, we'll just say, relative to voltage. So basically zero or low or no voltage effectively means 0, which is equivalent to logical false, or there is high voltage or some voltage for a simpler perspective, and that's equivalent to true. Now the reason I say no voltage or some voltage, it's not 100% accurate. 0 doesn't have to be no voltage at all, but effectively the hardware that determines the difference between a 0 or a 1 on any given line needs to be something that's very simplistic. Otherwise the device at large becomes expensive. Now you might think that it shouldn't be too hard to tell the difference between some value that's more low than it is high, and that is true, but it's definitely much easier to tell the difference, or it takes a lot less technology to tell the difference between basically no voltage at all and some voltage at all. And a way for you to test this is to take a butter knife and hold it in your hand, and you'll notice you feel no voltage. But then you stick it in the electric socket, and suddenly, whoo, you feel the voltage. No, don't do that. Don't do that. But that's the basic idea. It takes a lot less technology to tell the difference between none and some versus more or less low and more or less high. But it is, in reality, somewhere in between that. Now, when we have these different Boolean functions that we want to evaluate, we might have basic logical Boolean functions like and, or, exclusive or, and so on. But we already know what they are, so to perform greater operations in the computer, we need to synthesize more interesting operations like addition or subtraction or the comparison between two 8-bit values, that kind of thing. And so when we're creating these new forms of logic that aren't the core logical functions, or even if they are the core logical functions, one way we can describe how they function is through the use of truth tables. So here are two example truth tables. And truth tables will always have some number of columns that represent the total number of inputs to this particular logical function. Here on the table here at the left, we have a logical function called x1, and it has two inputs, a and b, each of which could be either a 0 or 1 at any given time. On the right truth table, we have just one more input, a, b, and c. And that's a logical function we'll call x2, and it's a function of a, b, and c. So when we have two inputs that can be either 0 or 1, we have 2 to the nth power, n being 2 here, which is 4, different rows that can represent each of the combinations that we have. Now each of those rows are referred to as a minterm, and I've got the minterm values listed here to the left of each table row in red. And those minterm values, like if we choose minterm 2 from the table on the left, we are going to find that we have a 2-bit input made out of a and b, that when we look at it as if it were an unsigned number, we get the binary pattern equivalent to that minterm. So if we're looking for 2, we should see the binary pattern 1, 0, because that's what 2 is. Now if we go to the one on the right, where there's 3 inputs, and we want to go to minterm 2, then we have to figure out what the 3-bit representation of 2 is, and that's 0, 1, 0. So instead of talking to one another about a row on a 5-input truth table that has 32 rows and describing it as the row where A is 1 and B is 0 and C is 1 and D is 1 and E is 0, we could just identify whatever the binary or the decimal equivalent of that binary 5-digit number is, and that's the minterm. So it's a shorthand way to refer to the rows. Each of these two tables has a column all the way to the right, and that's the output column. The output column represents the single bit value, or the single level value, 1 for true, 0 for false, or 1 for high voltage, 0 for low voltage. That is the output that will occur given this particular function when the pair of inputs or the set of inputs to its left come into that particular logical function or into the logical gates that represent that function in digital logic. Now in some cases, we see over here on the right, I've got this purple X. Now the purple part doesn't matter, or I guess it's magenta, but Sometimes you will see truth tables where individual minterm rows in the output have x's in them. And what that means is that particular minterm pattern, that set of inputs, A, B, and C in this case, cannot physically occur. And so we don't actually have an output for this function under that input pattern. And it may be because there is something exclusive about those different conditions. But whatever it is, it means that we should never expect A to be a 1 while B is a 0 and C is also a 1. That should never occur. And that's going to help us out later when we want to optimize the logic behind a particular circuit, because we can pretend that these unknown outputs could either be a 0 or a 1 to make our optimizations better. And it won't matter because which one we pick, whichever makes it better for us, because that particular input will never happen. So here are the truth tables for the basic logical functions that we build everything else off of. Over here, the AND operation. Remember that AND gives us a true value or returns a 1 whenever all of its inputs are 1s, or whenever all the inputs are true. So out of all 4 rows, only the row where each of the inputs is 1, which is the equivalent of minterm 3, 1, 1 is the number 3, that's the only output row that we're going to see a 1 in. Or on the other hand, only requires that a single one of its inputs, however many there are, be a 1, and then it will produce a 1 as output, which means it basically produces 1 all the time, and the only possible way that it could produce a 0 as output or false output is if all the inputs are 0 or false. Here is the not, or the inversion, and when we have a 0 come in, we get a 1 come out. We have a 1 come in, we have a 0 come out. When I was younger and first learned this particular logic gate and thought about its relationship to a physical piece of digital logic and how zeros mean low power or no power, or low or no voltage, and 1 means high voltage. I was very confused by this particular gate or logical function, because it would appear that when you send no voltage into it, voltage comes out. And so it was like a magic battery to me. Now, I can't explain how that works in the context of this video, but in a later video I'll show you how this works with actual power supplies, grounds, and transistors to route signals around. And then we can, in case you've got that same thought in your mind, we can solve this particular issue and see how it isn't really magic at all. There's always voltage involved, even when we provide none, apparently, through input. And then that'll give us an even better feel for how these truth tables and the digital logic level that we're looking at is really a step above. It's abstracted away from the low-level hardware quite a bit. So we as computer scientists don't have to be thinking constantly at the super low levels like our friends, the electrical engineers or the computer engineers. Now, down here on the bottom, we have the exclusive OR operation. And so when 1 and only 1 of its inputs are a 1, we'll get a 1 in the output. Otherwise, we get 0. So if both inputs are 0 here for a 2-input exclusive OR, we'll get a 0 as output. And if both inputs are a 1, as in this case, we'll also get a 0 for output. If we go to larger than a 2-input exclusive OR, you must be careful to determine whether or not that particular device that you're using, or the device that you are intended to be designing or laying out, is supposed to implement the 1 and only 1 policy, or the cascading exclusive OR style, where it's effectively giving a 1 for output whenever an odd number of inputs were 1. It's critical that we figure that out. But most of the time that we encounter exclusive ORs, they are 2-input only. The NAND operation is the same as the AND truth table, except in its output column, wherever we see a 0 in AND, we'll see a 1 in the NAND, because NAND is just the negation of the output of AND. It's the nodding of the AND. NOR is the same thing. So if we compare the output column of NOR to the output column of OR, we'll see that each row's output is the inverse of the others. Now, when we go to communicate a particular piece of logic, we're going to do this in one of several different ways. One way is with the truth tables. And the truth tables are great because they lay out, here's the set of inputs, here's another set of inputs, here's another set of inputs. And for all of those different possible sets of inputs, here's the very specific output you should expect to see. 0, 1, 0, 1, 1, whatever it might be, or impossible. And that's great, but if you think about an operation like AND or OR, in both of those cases, they have one output that happens almost all the time, and then the other output happens only once. So in the case of AND, you basically have 0 coming out of that thing all the time. And then under a special circumstance, you get a 1. So it's much more convenient to convey a piece of logic like that in a way that describes just the unique condition. For OR, we have 1s coming out 3/4 of the time, and then under the rare circumstance that we have all 0s as input, then we get a 0 as output. So it's much easier than to describe the OR function by saying it only produces 0 when all the inputs are 0. Now that's, of course, English, and it may not be specific or involve some kind of context that is sloppy when it comes to engineering. So we need another way to express these kinds of things. We're going to use Boolean algebra to do it. So our inputs to these circuits before were things like A and B, or in the case of the NOT, just A. And these are just arbitrary letters assigned to the individual inputs, so we know which input we're talking about. Now in the case of an AND gate, just as an example here, as I've got it on this slide, you can see that where we might normally have said it's the AND of A and B. Instead, we can write this as an expression, a Boolean algebra expression, that looks like algebraic multiplication. By just concatenating the two variables, A and B, we're expressing that the two of them are being ANDed together. And just like regular algebra, that multiplication feel, that multiplication-looking operation, binds tighter than things like addition. So whenever we're confronted with a long expression that includes Boolean ANDs and Boolean ORs, we'll know that the ANDs take precedence over the ORs. And then just like regular algebra, we'll use parentheses and things like that too. So we can describe AND as the AND of A and B as an A next to a B. We can also do this in a circuit diagram, a logical circuit diagram. These may seem to be less efficient than just the A next to the B. In the case of, say, an AND operation, it might be. But what we can do with drawings that we can't so easily do with algebraic expressions is show the functional relationships of components of the original expressions. And so by drawing logical gates and wires or signals going in and out of them and being routed to other places, we can visually follow the logic. And sometimes that makes particular circuits or particular functions easier for us to understand. And in the end, if someone was actually going to construct a real circuit out of logical gates, they might want to have a nice, accurate map to be working from. And the good thing is, all of these ways are equivalent. So there's an equivalent truth table for every piece of digital logic diagram that we produce, and then there's also some equivalent Boolean algebra expression for that. And so we need to learn what all of these different representations are so that we can move seamlessly between each to help us for whatever our purpose may be. To communicate something in an email, I love Boolean expressions. To communicate some fancy circuit that I don't actually know how to create, but I know what it should do, I might provide a truth table. When I'm ready to produce some kind of a circuit and wire something up, I may want to go over to a piece of digital logic, that kind of diagram. So let's go through the rest of these quickly. The OR operation, which takes two inputs or more, you're going to see that represented as a algebraic addition. So the plus symbol means or in a Boolean expression. And the digital logic diagram for it actually often looks a lot like the AND, but the primary difference is the but and the input end. It always has a curve, a concave curve going into the gate itself. Now the front in this particular diagram that I just took off Wikipedia has a pointy tip, but in a lot of diagrams it has a rounded tip. It's that curved input side that really distinguishes the OR gate. The NOT gate, or the NOT operation, is shown in Boolean algebra by the use of an inversion bar over the variable or variables that it applies to. So when I say variables, I mean we could have a Boolean algebra expression and we want to invert the entirety of the output of that expression. So we would draw a bar over the entire expression. But we can also draw a bar over a single variable, and it means invert that one variable. Now the digital logic drawing for this is unfortunately, I think, a little bit confusing because as it's shown here, this is the common version of a NOT or an invert by itself. There's a wire coming in over here, there's a wire coming out, and then in between is this triangular shape, which is not really a part of a NOT gate. It's something called a buffer, and it just indicates when we have a visual discrepancy in which direction the signal is going. We can see where everything is going. The same thing sort of works in the actual electronics. The buffer ensures the flow goes a particular direction. Not exactly the same as a diode or something, but we could just think about it that way at a very high level. And that's useful to us because otherwise the actual part that does the inversion in the diagram is this little circle, which we call an inversion bubble. So the inversion bubble and the inversion bar do the same thing. So here we have A coming down the wire, and the triangle really just keeps going in one direction, and then it gets inverted. If we didn't have that little triangle, we would just have a wire with a circle, and the wire is symmetrical and the circle is symmetrical, and then we'd have to apply a more contextual rule, like usually it goes from left to right, but maybe if they had to draw something weird, it goes from right to left. The use of that little buffer helps us out. Now, if we don't have a NOT in isolation, then we can just add the inversion bubble to a surface of another gate. And we see that in these first two on the right of the slide. So up here at the top right is the NAND gate. Now, a NAND is the inverse of an AND. So you see that we have A ANDed with B, and then an inversion bar over the whole thing. So that's the inverse of an AND, or the NOT of an AND, NAND. Now this is not the same thing. It is not logically equivalent if you were to work out their truth tables. It's not logically equivalent to the inverse of A ANDed with the inverse of B, where the inverse of A and inverse of B are calculated before the AND operation takes place. These are distinctively different truth tables because at least one of their output rows are not identical. So make sure that you don't accidentally try to indicate a NAND by putting multiple inversions over the inputs. That's incorrect. So a NAND gate looks like an AND gate, just like over here, except that its output has an inversion bubble. And because the AND gate has a clear direction because of the nose, or the front end of it, the output end, we don't need that little triangular shape from the NOT that we have down here on the bottom left. So we're not going to use that triangle unless we're doing an inversion in total isolation on a wire, which is not often. Over here, behind me, is the NOR gate. NOR, again, is the inversion of an OR of the input variables. And it looks the same in both the Boolean algebra version as well as the digital logic version. So it looks like A gets ORed with B, and then the whole thing of that is inverted because of the inversion bar. Similar to NAND, that is not the same thing as the inverse of A ORed separately with the inverse of B. Those are not the same. So in digital logic, here we have an OR gate, and on its output, an inversion bubble. So whatever came out of the normal OR just gets flipped. And then the outputs of the equivalent truth tables, the output columns flip just like we saw in the previous slide. The final operation we'll show a gate for is exclusive OR. So exclusive OR is represented in Boolean algebra with this symbol here, a circle with a plus sign in the middle. And so that means A exclusive OR B. And it's going to bind tighter than an OR, but it is not as tight a bind as an AND. So AND has the highest precedence here for what we see. Then we have the exclusive OR, then we have the OR. And additionally, there may be parentheses involved. Now, the exclusive OR looks a lot like an OR gate when we draw its gate in a diagram. The primary difference is that on the input end, an additional curve, which is spaced a little bit away from the curve of the OR shape, is drawn. And that's the giveaway that this is an exclusive OR. Now you'll notice I didn't include exclusive NOR on this particular slide, but just like the NANDs and the NORs, we can assume that we could fabricate an exclusive NOR by just having a couple inputs going into an exclusive OR gate, and then at the output of that exclusive OR gate, we could just insert an inversion bubble, and then we would have exclusive NOR. Now, when we define a particular piece of logic, either via a truth table, and then maybe we convert from that truth table down to a piece of Boolean algebra or some piece of digital logic that has an equivalent Boolean algebra expression, very often we may want to produce some other piece of logic, another Boolean expression, that isn't the equivalent expression, but performs the equivalent function. Or we might want to replace a piece of digital logic with an equivalent piece of digital logic in the sense that it performs the same function but has different gates wired together differently. Now the reasons that we want to do this are pretty simple. One reason is we might want to make our particular Boolean expression much simpler to look at or type in. Say if we wanted to send a text message to someone else that had a particular expression of a function in it. And that's great, but it may not be, if we have the shortest Boolean algebra expression possible, it may not be directly translated into the piece of digital logic that would normally implement that circuit. Now one reason for that is you may think we want to just use the fewest gates we possibly can. And at some level that is true because fewer gates use less power. And then fewer gates allow us to put things together more closely, which means less power, smaller distances, faster computers, fewer things might also sound like they might be cheaper. But they may not be, and I mean inexpensive. It may not be, because we may have to buy lots of different types of gates, and in mediocre quantities of each, to produce the total logic of our system or our component. Now, if we can use logical equivalencies to take something that makes perfect sense in digital logic, that clearly makes a particular function happen, but it uses, say, 3 or 4 different types of gates, if we can use the logical equivalency laws to convert such a circuit into one that uses not necessarily fewer gates, but fewer varieties of gates, and maybe greater numbers of gates, we can then buy 1 or 2 gates in very high volume and reduce the cost of the computer, even if it also makes that computer just slightly larger or have to use more transistors. Remember, we are really compacting the number of transistors we can put into a particular space. And so at some level, while we always want to be careful and efficient in how we deal with that space, we now have absolutely run into the problem of having a human mind figure out what to do with the extra transistors that are in the same space. I mean, imagine being at a facility that produces some electrical component and everyone's patting themselves on the back because they made this great thing and they got it all to fit in this nice little chip that has 100 million transistors in it, and wow, I can't believe we did it in 100 million transistors. That's great, pat yourselves on the back. But don't forget, in like 18 months, you're going to have the same size package that has like 200 million transistors in it. And it's not quite a given that the people who just 18 months ago were able to very cleverly come up with this thing that used 100 million transistors. They're not necessarily going to become able to come up with something that's fantastic using 200 million transistors, right? At some point, we're there, the rate of the growth of the transistors, the number of transistors extra that we get in the next little iteration of transistor density gives us the leeway to use fewer and fewer types of gates. And so we can do things in volume, potentially, that make the device less expensive without dramatically decreasing the performance of the system. So we have to think about those things. And these logical equivalence laws will help us deal with that. So I'm going to just quickly breeze through these because my expectation, at least based on the students in my course and the prerequisites of this course at the university that I teach at, because of those, I assume that you've already taken either a discrete mathematics course or a finite mathematics course in which you've looked at these kinds of logical laws relative to propositional logic. So this should be review. I've just recast the way they look in terms of the Boolean algebra expressions that we will use here. So there's the commutative law, and that says that we can take things that are ANDed together and reverse the order that they show up, and it doesn't change anything. The same is true when we OR things together. We can reverse the order of the operands, and nothing is different. The associative law tells us that when we parenthetically bind a part of a series of the same operation, whether it's AND or OR, that we can change where that is bound. So we can move the parentheses effectively left or right as long as we're within the same series of operations. The distributive law, much like the distributive law in regular mathematics or algebra, is going to allow us to take something like this A and distribute it into this parenthetical OR. So A ANDed with this OR of B and C is going to be the same thing as what looks like A times B plus B times C, just like your early algebra class. But it functions slightly differently. It means it's the same as A ANDed with B or B ANDed with C. This is a terrible mistake. This should say A ANDed with C. So I'll need to correct this on the slide later. But please note, this should say A ANDed with C. Definitely not B ANDed with C. This is totally wrong. I'll have to change that right now because I can't deal with it. There we go. A ANDed with C. There it is. All right. In the right column, the OR form of the distributive law says that if we have OR ANDed with two things that are ANDed together, we can take and distribute the left side of that OR into these things that are ANDed together so that we still ended up with something related to B ANDed with something related to C. They just are each individually ORed with A, the left-hand side of this. The identity law tells us that if we AND any variable with a 1, then we are going to get that variable, whatever that variable's value was, as output. If we take any variable and OR it with a 0, then we are also going to get whatever that variable was out of it. The negation law tells us that if we take anything and AND it with the inverse of itself, we will get 0 because it effectively says that one of these must be a 1 and the other one must be 0. So a 0 ANDed with a 1 is always going to give you a 0. In the OR column, we see that if we OR something with the inverse of itself, we will always get a 1 because since one of these is a 0, the other one must be a 1. And if you OR anything where one input is a 1, at least one is a 1, then you're going to get a 1 as output. The idempotent law is going to show us that we have, if we have the same thing ANDed with itself, we're going to just get the original variable out of that. If we OR something with itself, it's the same as itself. The absorption law says that if we take some variable A and OR it with some expression where A is involved ANDed with other stuff, that's still going to be equivalent to whatever A is. Similarly, if we take some variable A and AND it with itself ORed with something, that's just going to give us A as well. De Morgan's law, you'll sort of notice immediately looking at this that we have these split expressions with the inversion bars over them. This is much like what we saw on the previous slide. So be aware that this row really shows us how we can correctly split or combine inversion bars. So if two things are ANDed together and then inverted, we can split the inversion bar between the two variables, but we have to convert the AND to an OR. In the opposite direction, if we have two things ORed together and the result of that is inverted, we can split the inversion bar between the two variables by converting the OR to an AND. The final law that's on here doesn't really have a form for AND and a form for OR. It's just the double negative law. Effectively, it says that if you have a variable and you invert it and then you invert that, you're going to get the same thing that you started with the original variable. So the double negative just puts you back where you were. So in this video, we looked at the basic ways that we can write common logical operations in Boolean algebra, how those same operations are reflected in truth tables and how truth tables work, and how we can use min terms to quickly identify a row in a truth table. And we've looked at how both the Boolean expressions and Boolean algebra expressions and the truth tables have some equivalent piece of digital logic associated with them. And we looked at the core digital logic gates for those core pieces of Boolean logic. Finally, we looked at the logical equivalency laws and briefly discussed the advantages of taking something that already provides the correct function and altering it with the equivalency laws, either to make it more efficient in the total number of gates or the compactness of an expression, or to make it more efficient in terms of how many different varieties of gates it uses, so that we can reduce the cost of our systems by buying in volume.